So thanks everyone for joining us today. I'm Charles, this is Nick. We are both members of Compute Platform and Netflix. Today we will be sharing how we use Kubernetes to manage the Netflix computer infrastructure and how we perform dynamic capacity management on top of it. Today's talk will be divided in two parts. So first, I will give you an overview of our system and walk through each layer of our stack so you can get a clear picture of how everything fits together. Then Nick will dive into the mechanisms we developed on top of this platform to manage the cloud capacity. So before I dive into the system, I wanted to introduce a term you will hear a lot throughout this talk. Since I assume most of you are familiar with the basic Kubernetes concept, I would like to focus on something specific for Netflix, which is Titus. So Titus is our regional API that everyone at Netflix use to launch container workload. Unlike some organizations, developers at Netflix don't use the Kubernetes API directly. All workload launch goes through Titus. So Titus API has been around for over 8 years. It originally sat in front of Mesos before we migrate to Kubernetes. At the heart of Titus is a concept of Titus job. You can think of Titus job as a specialized type of Kubernetes workload, similar to deployment or job, but with custom business logic tailored for Netflix. I think one of the most important lessons we have learned during the past 8 years is that most developers don't really care about Kubernetes specific concepts. What matters to them is whether their job or container can be launched and run their service. This fundamental requirement has been there since day one of Titus API. And even though we switched from Mesos to Kubernetes, this API layer has remained largely unchanged. As you will see throughout this talk, having a unified API layer like Titus can greatly simplify the overall system architecture and make managing large fleets much, much more easier. So now let's dive into the system architecture, starting with our fleet topology. So at Netflix, our cloud infrastructure is built on top of the cloud provider and spans multiple regions. In each region, we operate a fleet of Kubernetes cluster. However, we don't provide a single unified entry point across regions. So when users want to launch containers, they need to specify the region where their workload should run. Within each region, though there is a unified entry point for submitting workloads, we organize our cluster into 3 categories. Service cluster, this runs our critical long-running service. Batch cluster, these handle short-lived batch jobs, such as streaming, encoding, or decoding workloads. And the trough clusters. These are made up of machines that temporarily borrowed from unused capacity. Some of our workloads still running on EC2, so some of them are not used their capacity. We can borrow them, put it into this cluster. So this resource can be reclaimed by their original owner at any time. So users of the trough cluster should expect their job to be preempted at any time. We separate the batch and the service workload into 2 different clusters because their launch patterns are so different, which require different configuration of both the control plane and date plane components. So for instance, batch workloads often come in bursts, requiring rapid scaling across nodes and generating steep I/O pattern on etcd. This can impact the overall performance and the launch latency of all the workloads, which is especially critical for our long-running service. But this setup doesn't mean we are going to waste the resource that is not being used on the service cluster. We have a cross-cluster trough mechanism to make use of spare capacity on the service cluster, and Nick will give more details in later of this talk. Okay, so let's dive into our architecture. So what does our overall system architecture looks like in each region? As shown in the diagram, every region starts with a regional Titus API gateway. Remember, we don't expose the Kubernetes API directly, so all requests must go through this Titus API gateway. When a request hits the regional API gateway, it's forwarded to the federation control plane. This is the core components at a federation level, responsible for routing traffic to the most suitable Kubernetes cluster. The federation controller is connected to a meta Kubernetes control plane, which stores fleet-wide capacity management setting and workload routing rules. The router then selects the best fit Kubernetes cluster and forward the request to our cellular API gateway. At Netflix, we refer each Kubernetes cluster as a cell. The cellular gateway is another Titus API gateway, which cache the latest Titus job status in memory and perform early validation to ensure the job definition is correct. It also handles queries for complete jobs. We're using Cassandra as the data store for job definition. Next, the job definition is sent to the Titus job coordinator, a controller with an API handling, request handling layer. The job coordinator reconciles the Titus job, create the corresponding Titus task, and then these are launched as a Kubernetes pods. At the same time, the job definition is stored in our global Cassandra data store. So we choose Cassandra over etcd for persistent data for two main reasons. It is reliable. So Cassandra is generally more reliable for persistent data than etcd, since etcd is designing for temporary metadata rather than large long-lived data sets. And it is more scalable. We need to keep job definition even after job have complete. And we'll keep those definition for 2 weeks or even longer. So which requires significant storage. etcd typically used only for active workloads and has an 8 GB storage limit. Once the pod is created in Kubernetes, we use a scheduler with our custom plugins to place pods on nodes and webhooks to mutate and validate pods as needed. For capacity management, we organize different instance types into separate resource pools. An in-house controller called fleet management scales the agent fleet up or down and periodically defrag the resource to improve the efficiency. So that's the architecture. You might notice that our system looks fairly straightforward, and that's the intentional. It wasn't always that simple, but we have spent a lot of time streamlining and simplifying the architecture to get to where we are today. So if you can hoping to hear about some secret source or cutting-edge tricks that Netflix use for run their Kubernetes cluster, you might be a little bit disappointed because we are here to present anything. We're not here to present anything sophisticated or high-tech. Instead, our talk is focused on sharing some real-world lessons we have learned from managing large fleets of Kubernetes for 8 years. So at Netflix, our engineering team is relatively small. So our top priorities are reliability, ease of use for developers, and minimizing operational overheads. So after years of running Kubernetes at scale, we have discovered that simply following the official Kubernetes runbook and only adding the necessary components to put things together is usually enough. Instead of building a very complicated or sophisticated system, we have found that a simple, straightforward architecture can deliver solid performance and meet our business needs just as what we want. If there is any one takeaway from this talk, it's that you don't need to over-engineer your setup by sticking with the default Kubernetes configuration, following the best practice, and only adding essential glue components. You can support critical large business just like Netflix. So let's talk about cluster federation. When our workload grows large enough to hit the Kubernetes scaling limits, around like 150,000 pods or 5,000 nodes per cluster, we naturally need to spin up new clusters and distribute workloads across them. However, the open source community still hasn't solved the federation challenge in a universal way. The main reason is that every organization has different requirements for federation. For example, some teams need to optimize workload placement based on rare hardware type, especially if they are running cluster across multiple cloud providers to find the most cost-effective resource. Others, just like Netflix, need to federate Kubernetes cluster to handle massive scale of business needs. Because each use case has its own priority, there is no one-size-fits-all architecture. Throughput is our highest priority. And we also aim to manage fleet-wide capacity via the federation layer. Since we expose Kubernetes infrastructure to users through the Titus API, we don't need to worry about support many different kind of workload or complex placement scenario. However, given this requirement, we found that none of the existing federation solution met our needs. They either doesn't scale well or were too complex to maintain. So that's why we built our own federation solution, and it only do two things, and we try to make this do these two things well. The first, it will route the workload to the right cluster. Second, it manages the resource capacity across the entire fleets based on the real-time usage and traffic prediction. Here's how it works. As shown in the diagram, our federation service runs multiple instances, just like other federation solutions. It uses a Kubernetes control plane to store metadata, but to achieve high throughput, we made it stateless. Each instance runs its own router process in parallel without storing the job status in the federation etcd cluster. At our scale, it's simply not feasible for us to keep all the workload metadata in the etcd. While parallel routing sometimes means we don't always make the perfect global decision, but our very large fleets give the underlying scheduler enough flexibility to correct any suboptimal choice. We still keep the job status, but in a more efficient way. Instead of watching the Kubernetes API server of each worker cluster directly, we leverage the Titus API layer, which already caches job status in memory. This lets us monitor job efficiently without overloading the Kubernetes API server. So for capacity management, each Kubernetes cluster maintains a summary of its resource usage. We track which app are using which instance type and combine this information with prediction from Netflix global traffic forecasting service. The federation controller then dynamically adjusts the capacity of each instance type in every cluster. This summary data is small, so we can just watch it directly through the Kubernetes API server. We have been running this system for years with great results. The code base is really small, just a few thousands of lines of code, and it's stable, with very few issues or operational headaches. The biggest lessons we have learned is to be clear about your top priority from day one. In our case, that was high throughput job routing. Even if it means trading off some placement optimization, and wherever possible, decide your global components to be stateless, rather than relying on a single data store like etcd in a Kubernetes control plane. So for in-cluster scheduling, we use just the open source scheduler framework with our own cluster plugin and the various scheduler profiles such as bin packing, spreading out, and again scheduling. We have found that the plugin hook provided by the scheduler framework usually just sufficient enough to meet most of our business needs. So for example, for service workload, we use the bin packing, and we use some of custom plugin like queue sorting, pre-filter, custom filter, post-filter, and the reserve plugin. And the rest of the plugin in this profile, we just use the Kubernetes default plugins. And so these are some of the key components of our system. I hope this gives you a clear picture of how everything fits together. Next, Nick will explain how we manage the capacity using this platform.
Hello, everyone. I'm Nick Parker. So I'm going to talk about capacity management. This is kind of the second half of the presentation. And there's, I guess we can just get started. So at a high level, I think of capacity management in Titus as kind of a balance of these three things. The first is cost, or cost efficiency. I mean, in an ideal world, we'd be running as much workload as possible and spending as little money as possible in the process. Meanwhile, from an end user's perspective, some of them care a lot about launch latency. They want to start as quickly as possible. Others don't care as much as long as it's within reason. Similar story with disruption tolerance. We run some stateful services that don't want to be touched ever, ideally. Other services are okay with it, again, as long as it's within reason. We support these different balances while trying to maintain kind of a common code base with some difference in profiles and that sort of thing. One of the ways we kind of manage those different use cases is through these three kind of priority classes or tiers. And these are like Kubernetes priority classes, and we use these as signals in a few places. But as far as capacity is concerned, the reserve tier is basically pre-scaled capacity. We keep warm nodes around, and reserve services are placed on those nodes. Elastic services can use existing nodes if they're available, but otherwise we'll scale up some nodes to fit to meet their needs. And then the third tier, like Charles had mentioned, we have the trough tier. This is kind of like spot instances for pods, where we don't scale up for these. If we don't have free space in the system already, we're not going to add more nodes for them. But when that free space becomes available, they can fill that free space and basically act as kind of a cost recovery mechanism to make up for waste that we otherwise would have. Out of the 3 tiers, only trough is preemptible. And this is a customization that I've upstreamed into Kubernetes. So in particular, like reserved will not preempt elastic, but both reserved and elastic can preempt trough. So let's start talking about auto-scaling. It's a bit complicated. I've got it split across 2 slides. For this first slide, I'm going to talk about like the nodes themselves. We have kind of a 2-stage process. So the first stage we call, and it's driven by taints. So we just use no schedule taints. The reason we use those instead of no execute is it gives us more control over the teardown process. And the reason for all this complexity is because we have custom disruption budgets that kind of predate the Kubernetes one, but that'll be on the next slide. Anyway, in service of those disruption budgets, the first phase is scaling down. So this is kind of a normal, like we've cordoned off the node. We're not letting new things run on, except for trough. We do allow trough to run on these nodes while we're waiting for them to scale down. The difference is we can be waiting days, even weeks, for a scaling down node to finish. So we're kind of making the best of it by allowing trough to run there. And also that process is reversible. If later on we have a pending pod that looks like it'll fit on a scaling down node, there's nothing wrong with the node itself. It's just at some point in the past we decided we could get rid of it. Now we can change our mind and untaint it and make it available for that incoming workload. This saves us it saves the pod time, it saves us money and not scaling up another node. It's kind of a win-win for everybody. A little bit more about scaling down. We have this kind of defrag, kind of mark and sweep process. It's kind of simplistic internally. It's basically just saying, all right, well, we're overscaled by 30 nodes. Let's find 30 good nodes to get rid of. So it might be something, and that's kind of based on a scoring system. So we'll say, all right, well, this node looks like we can get rid of it in an hour from now. This other node looks like it's going to take a day. We'll use some points to say the 1-hour node should get selected for defrag. The next stage is evacuating. So that's basically after all the normal pods have left, we'll switch to anything that's left on that pod, or sorry, on that node. We'll terminate all the trough pods, and then we'll get rid of the node. You can skip the scaling down state in the case of an unhealthy node. So we use the Kubernetes node problem detector. If we have a failed node, like something that looks like it's permanently busted, we'll try and terminate all the pods ASAP. And like kind of skip the scaling down stage. And the chart on the right, it's a bit blurry, but that's just kind of indicating like the state machine here. All the stuff I just explained, it's the same thing. OK, so now looking at the pods. So I mentioned earlier we've got these custom disruption budgets. They kind of predate Kubernetes disruption budgets. They've got kind of a confusingly similar name, but they have additional modes that Kubernetes doesn't have. And sometimes that's for better, sometimes that's for worse. For example, it's not technically in the disruption budget itself, but all batch jobs that come in, we actually have them set a time limit for how long they think they're going to run. So a batch job might say, oh, there's no reason I should be running past 48 hours. We'll actually use that as an input, both for where we schedule that pod, as well as for this teardown process, where we can use that as an input into like determining an ETA for when a node could be torn down, when we want to scale down a surplus of nodes. There are also some painful options. For example, we have this option called guaranteed uptime, where basically when a pod comes up, we give it, or it will specify a minimum duration where we're not allowed to touch it. It could be hours, days, even weeks. It can be a very long time. And so we really try to cordon those off kind of in a corner, separate from everything else. But that also can be used as an input into our ETA. We can very predictably say, all right, well, this pod set a 5-day guaranteed uptime. It's been running for 3 days, therefore we have 2 days left. Like that's the math. It's not that complicated. The evaluation of this is kind of its own 2-stage process. The first thing we check is those sort of stateless things where it doesn't involve the job health. It's just like, oh, did they have a guaranteed uptime? Do they have a batch time limit? Does one of those say that we need to wait until sometime in the future? If that rule passes because they don't have one of those things, or that time is in the past, then we'll go on to the stateful evaluation where we'll say, oh, this pod wants like 95%, or this job wants 95% of its pods to be up. And if we terminated this pod, we would be exceeding that limitation, so we won't touch it. So once something is past both of these checks, then we would terminate the pod, and that would bring the scaling down node a little closer to being cleaned up. Okay, scaling up is a bit simpler. We just have this one slide for that. So there's two sources of scaling up. One is the reservations that I talked about earlier. There's two sources of scale up from there. One is a config change where the reservation has been grown either by us manually changing it or through an automated process auto-adjusting the reservation itself. Or if an elastic pod, oh shoot, I just realized I may have missed borrowing. I don't remember. The idea is we can allow elastic pods to run on reserved capacity. It's kind of like borrowing that capacity, and then we realize that we have that shortfall. We scale up the reserved space afterwards when we see that there's a shortfall, and that can cause the scale up through a reservation. We only allow that, it's worth pointing out, for nodes that we know we can make up the difference later. So for example, if it's a difficult to obtain GPU type, we don't allow borrowing in that case. The other reason that we can scale up is for pending pods. The logic for this is pretty similar to what Carpenter does. I don't remember off the top of my head if this is identical, but the logic that we have is first we check only for pods that have failed at least one scheduling cycle, because that kind of indicates that all the current nodes in the pool in the cell don't work. If that's the case, we first check for any scaling down nodes that look like they match according to any affinities or other rules that the pod might have. We actually just kind of import the Kubernetes scheduler libraries for that. And then if we can't find any scaling down nodes that we can untaint to make that pod get unstuck, we'll fall back to actually scaling up another node. And we have a little bit of logic around if we have a bunch of pods, let's say we've got 20 pods, we try and estimate how many nodes we need to service those 20 pods. It can vary because sometimes pods may have pod affinity rules against each other where they can't be co-located, and so that affects the math. Anyway, we try to estimate that when we're getting the additional nodes. Okay, so I mentioned earlier, actually both of us have mentioned earlier about trough. It has some effect on our capacity management in that we want to keep track of how much free space there is available for trough. The reason for that is we advertise that free space to users at kind of a region level, so across the cells in that region. And we'll basically say, it's kind of like an offer. We're basically saying, we've got this space available, nobody else is using it, you could send us some trough. This kind of acts as like a honor system back pressure in a way. Like those clients are expected to not send us stuff. Happily, we're in a world where we just have internal clients within the company, so we can tell them to knock it off if there's an issue. But anyway, the sources of that free space include scaling down nodes, unused reservation space, that kind of thing. We also will scale. We have separate pools that were kind of implied in Charles's diagrams around EC2 capacity that we're not using somewhere else. We'll scale that up here and then like fill it up with trough pods. And then if somebody else needs those nodes back, we'll terminate all those trough pods, we'll preempt them, scale down those nodes, and kind of give back the capacity. But ultimately, trough is we just need to get a number for how much free space we have, and we advertise that to people and just kind of keep track on a like every few seconds, refresh the number kind of basis. Okay. So one thing that's worth pointing out with all this is that like a lot has changed in the system already. Like if we were doing this presentation a year or two back, this would actually be pretty different. A lot of the concepts would be the same, but we've been doing a lot of cleaning up, and we are investigating like things that we are doing in a custom way just through the process of a system that's been evolving over several years and even predated Kubernetes. For example, we're currently relying heavily on auto-scaling and bin packing as much as possible, trying to keep everything in as small of a node pool as possible. We could switch to just targeting fixed nodes, flat fleet with like a target percent utilization, completely flipping that structure on its head. We've been currently running like our node management with these custom resource pools. We've been thinking of moving to Carpenter for that, but maybe I mean, given our disruption budget rules, we may need to customize some things there, but we're investigating. And then we've also been thinking about just like getting rid of reservations entirely and instead focusing on QoS and keeping a minimum number of nodes around and not worrying about like maintaining this quota system. So nothing here is final. Maybe in a year from now, this presentation would be very different. And that's it. So I guess thank you very much. This is Charles Zheng, and I'm Nick Parker. One last thing. We are hiring. So there's this QR code. There's also a flyer down on the boards, like the job board down the basement. So if anyone's interested, go take a look, or just go to jobs.netflix.com. But otherwise, I guess we're open to questions. Looks like we have about 5 minutes. Yeah.
How much capacity
So on trough, I don't know off the top of my head. I mean, it does kind of vary. Just to go back to this slide, like you can see that like the blue number there is kind of like going up and down. It's on the order of like thousands of nodes worth, where a given node is like a 24XL, like that kind of scale. I mean, it varies a lot day to day. And normally we run stuff that's, oh, right, just to repeat the question, you're asking about trough capacity, what kind of numbers we were dealing with, and what kind of workload. And as far as the workload, in Netflix, something we do a lot of is encoding video, and a lot of that isn't urgent. So that's a big user. There's a bunch of other stuff too, but that's kind of a major user on that. So, okay, I guess. We got a hand up. Yeah.
You said you talked about the federation, regional federation things, and where like solutions existing did not fit the bill. Are you going to open source any of that?
The regional federation solution, right? We are not planning to open source it because as I just mentioned, the number of lines of code is very small, just like thousands of lines of codes. And we just share the basic logic of how we implement it. I think anyone from any other company can easily copy and re-implement, yeah.
It's also worth pointing out that a lot of the federation is based on the Titus API itself, because the cells expose the Titus API. It's not a generic Kubernetes federation, I guess. That also, for the record, that makes it a lot simpler, because we don't have to implement like watches across cells or anything like that.
Yeah, I think someone.
Hi, thank you for the session. I'm curious how you guys track like underutilized deployments or daemon sets. I'm just curious how you guys like right size containers. Any thought on right sizing containers with like VPA or any tool at your scale? That would be great to know. Yeah.
As far as I know, like you mean in terms of like going to a user that's like not utilizing what they're asking for,
yeah,
that kind of thing.
Yeah, like right sizing CPU memory requests.
Right. So we don't do anything automatic. Like when somebody submits a job, they do get to specify how many CPUs and how much memory, how much disk, how much network, how many GPUs they want, and we just kind of take them at their word. Like we don't auto-size anything on their behalf. Usually that's kind of, we reach out to that customer and say, hey, you're way overscaled.
So we have some undergoing work. I don't want to say this work for my colleague. My colleagues are here, long-time folks. They are doing the right size container. So if you have more follow-up question, I'll route you to Jose, who is drive the work. Second line.
I'll get his contact. Thank you.
Yeah.
Thank you for a good presentation, guys. My question related to the bin packing fragmentation. How do you handle proper bin packing when you have short-lived and long-lived tasks? You eventually end up with not fully bin packed nodes. How do you handle it?
It's kind of echoing here. You're asking about short-lived versus long-lived pods and disruption budgets?
No, not disruption, bin packing, fragmentation. So you eventually end up with nodes that are not fully bin packed.
I can't hear it. I don't know.
Yeah, I cannot hear it clearly. Maybe.
I probably can come to you and ask.
Okay, I'll answer what I think you're asking, which is like, how do we separate those or organize them? Okay.
GPU workloads or CPU workloads?
Both. Oh, okay.
So for GPU workloads, you eventually end up not completely filled nodes, right? Because you have short-lived tasks and long-lived tasks. Handle bin packing.
I think you can ask your question.
Okay. The question was, on GPU nodes, how do we handle a mix of short-lived jobs and long-lived jobs? Yeah, and the bin packing on GPU nodes. At the moment, I wouldn't say it's completely solved. We do have cases. So I think at the moment, a lot of what we do is just, we have pools for specific customers, particularly for GPU nodes. GPU nodes are kind of special just because they're not infinite. Like we usually have a finite number of them at any given time. So often we'll have like per customer pools of a few GPU nodes that apply to that customer. Because we do have a problem of like, I mentioned earlier, we have like our reservations are kind of aggregate resources, which doesn't work well with GPU nodes because you might have like, oh yeah, you reserve 20 GPUs, you're currently using 12, so that in theory you have 8 available. In the current accounting system, those 8 might be just distributed across multiple things. So if you have a single job that wanted 4 of them, it might not be able to get them, do that fragmentation effect. So that's kind of a problem right now, and we've been sort of working around it by at least saying, all right, well, you as a customer, you get these nodes, they're just dedicated to you, and if you have this, and that at least kind of reduces the scope of the bin packing problem. Like you don't have some other random team like eating into someone's capacity. That's kind of how we deal with it right now.
Time's up.
Oh, okay. Are we time to go?
Yeah, one question.
I can take the question offline.
Yeah, how big is the cluster like for this scale of the application like Netflix? How many nodes you have it in the cluster? What's your biggest cluster, and how we are maintaining the cluster upgrades with different Kubernetes versions, etc.?
So it sounded like how many nodes we have in the clusters?
Yes. How many nodes? My question is basically like, is that big clusters or the small clusters, multiple clusters? Like how is your topology? How big is your cluster?
Yeah.
So I think I mentioned before, we try to control the size of the cluster under the limitation of Kubernetes official scale limits, which is 5,000 nodes, right? But in some of the cluster, we have a very large nodes. We have metal machines from AWS. So for those cluster, we have smaller size. It really depends like instance type.
Okay.
Yeah.
Okay. And are you maintaining, like how you are upgrading? That's what I'm interested, like you have such big cluster. How you are maintaining upgrades, etc. on the cluster?
Sorry, I cannot hear you clearly. Maybe I can answer your question offline. We are up time. Yeah. Thanks. Cool. Thank you.